All right, hello everybody and welcome. We'll probably wait a couple minutes here before we get started. I'm still seeing a lot of people trickling in here on the attendee list. In the meantime, please try out the Q&A tool. It's a little chat looking bubble thing at the bottom of the Zoom window. Let us know where you're dialing in from. It's always nice to see and lets us know that everybody's getting a chance to find that tool. Quite a few different people dialing in from Germany as usual. I'm seeing Paris pop up a couple times here too. It's nice to see. I'm connecting here from Austin, Texas. Anybody from that part of the world? All right, we waited a little while. We'll get started here. Welcome to the webinar. We're going to be talking really about the Fourier Transform today, but the whole big picture is going to be about how we can build a classification model on a time series signal, an IoT data source. So my name is Corey Wiesinger. I'm a data scientist with NIME in Austin, Texas here, and I mostly specialize on time series analysis applications. If you follow that kind of stuff, you've probably seen some of my blogs and things like that around. And I've also got my colleague Marit here with me today, who's going to be helping me walk through an example and some of this information.
Thank you, Corey, and hello everyone, also from my side. And yeah, I'm also a data scientist at NIME in Constance, Germany, and I'm also specialized in time series analysis in teaching. And yeah, I think, Corey, we can start.
Right. So first things first, I just kind of want to recap on some of the logistics. So we're going to be kind of going through the webinar for the first 45 minutes or so, and then we'll have 15 minutes at the end for Q&A. So please do use that Q&A tool. When we can, we'll try to answer them live as we go. But if questions are kind of more tangents, if you will, we'll come back to those at the end. So please do use that. We'll make sure to address them as best we can. The session will be recorded. We'll be pasting it to YouTube shortly. And the slides will be available, and the workflow that we're going to show you will all be available. And the easiest place to go find those will be on the NIME form, but you should be getting a follow-up email as well. Okay. So with that, what's our agenda? So we're going to start by kind of introducing the concept of data transformations. We're going to introduce what the Fourier transform is, where it takes us, which is the frequency domain, why that's useful, what kind of industries use this Fourier transform, how to do it in NIME, of course, and then how we can build a model on that transformed data. And then finally, we'll wrap up with some questions. So with that introduction out of the way, you want to show us the example, Marit?
Yes. Okay, so let me start with the workflow. And as Corey said, the example use case today is classification on time series data. So what we do audio signal classification. And the workflow, for those of you who already have been building NIME workflows and doing machine learning applications, I think it looks very familiar. So you have here data access, you have data preprocessing, you have model training and model evaluation, and some data exploration. But in this webinar, we are going to go a bit more in detail into the preprocessing here, where we have the Fourier transform and how we can make a time series or signal data into a classification use case. So I start now with this data access here, and this is the data that we have, the raw data, and it's 4 numeric columns, and we have named them 1, 2, 3, and 4. These are actually 4 different musics from four TV shows. So maybe, Cory, you have something to say about what is this data actually that I have?
Yeah, so I think before we get terribly far into the Fourier transform and the application today, it's good to kind of recap what an audio recording is from a data perspective. So what we're looking at when we're looking at audio data is we're looking at pressure recordings, right? So a sound wave is just pressure over time. So to record audio data, we just sample the pressure many, many times per second. So that's where you'll see things like what's a normal sampling rate for an audio recording, 5,000 hertz or 5,000 kilohertz or 18,000, 25,000, depending on the application, right? So usually we like really high fidelity recordings for our music that lets us hear higher frequencies. And that's kind of what we're looking at here, right? We're just looking at these pressure recordings sampled over time. So if you look at the top of this view right now, you'll see that there are about 7 million rows in this table. And that's a lot of rows, but there's only a few columns and they're numbers, so it's not too bad to work with. But that's what we're working with when we're talking about raw audio data in this kind of way, is we want to use these raw files, which are basically just imported wave files, if anybody's familiar with those.
Okay, interesting. So as a time series, I can recognize it. So it's a numeric column, and here I have the time progression from top to the bottom. But today we have a classification use case. So we need some kind of a transformation. So we need the predictor columns and we need the class column. So this is actually what is happening here in the data transformation, and the Fourier transform is a part of that. So before I open the component, before I explain the workflow steps, I would give over to you, Cory, and you explain what the Fourier transform is.
All right, thank you, Mara. So before I talk specifically about the Fourier transform, I just kind of want to recap what is a data transform, because sometimes this term can be intimidating. When we're talking about data transforms, really we're just changing the representation of the data. So if we do something like, for example, you might be familiar with talking about a point on the plane. Maybe we'll use an XY pair for the Cartesian coordinates, or maybe we'll like choose an angle and then a radius out, and we'll use like polar coordinates. These are just different ways of representing the same data. So these transformations are kind of all over the place in data science. They're super helpful. They let us kind of look at the same data from different angles and perhaps allow us to see different features with more clarity. And what the Fourier transform does is it lets us see frequencies more clearly. So that's kind of what we're looking for here, is we're just applying a transform that kind of shifts how we interpret our data and hopefully gives us a better angle for viewing information from it. A lot of useful transforms are reversible, and the Fourier transform in its raw state is a reversible transform, but there is a bit of a loss there in what we're going to do today. So when we talk about the transform today, we're not going to be able to necessarily take that and recreate our signal perfectly, but hopefully we'll be able to extract the main features of it and use those in our analysis. Okay. So with that out of the way, now let's talk a little bit about what the Fourier transform is. So what I've given you here at the top is the equation for the discrete Fourier transform. So the original one is similar, but instead of having a summation here, we would have an integral, and it would be a continuous transform. So the original one was a continuous transform with an integral, but the discrete one that we're typically going to use, since we have data points in this way, will be this equation. An interesting fact, actually, is that the Fourier transform was originally contrived 200 years ago now. It was 1812 or 1822, I believe, when this was first invented. And I believe he was using it to calculate trajectories of planets. But we're not going to focus too much on that. Just happy birthday, Fourier transform. But what the Fourier transform is doing here, and it's kind of difficult to see just looking at this equation, but when we look at this complex exponential here, this is just a generalized version of sine and cosine waves. Because if you're familiar with Euler's identity that says e to the I pi is cosine plus I sine, or maybe I'm switching those backwards, but that identity allows us to kind of switch back and forth. And for that reason, we use this complex exponential here. So what I want you to imagine here when you look at this is sine waves. So these are just our waves. Xk here is just our raw values. This is our original signal. X is our original time series at timestamp k. So this is the kth value in our time series. So what we're really doing here is we're taking this sine wave, we're comparing it to our series with this dot product, saying how well does it match up? Are these values really close together? So if my sine wave is high when my series is high, and my sine wave is low is when my series is low, it kind of matches up, the pattern kind of connects there, and I apply a strong amplitude because of this equation here. So this kind of gives us the amplitudes for our component sine waves. So that's what we're going to do walking through here, is we're looking at how well all of these different sine waves match up with our original signal, and we're applying their magnitudes that way. So this is really useful because if we do this enough times and we use enough sine waves, what we get is a new way to represent our original signal. So originally it was just what Mart showed you in that view, just one long series of numbers. But now we're saying we can re-represent that series of numbers as the sum of different sine waves. So that's what we're doing with the Fourier transform, is we're re-representing some unknown signal as a sum of different sine waves with varying frequencies. Okay. When we look at the amplitudes of those component sine waves, those sine waves that we add up to recreate our signal, that's when we're looking at the frequency domain. And this graphic might be more helpful to visualize that. So let's say this is our original signal with a line plot here. We can kind of look at these different sine waves with varying frequencies as we go down, and we can say, how strongly does this sine wave match up? What amplitude do I want to use to make this one fit through this? So then I see that this is a large sine wave. And then I've got this one being a little bit smaller and this one being a little bit smaller. And those tell me how strongly each one of these frequencies appear in my original signal. And the idea is that then if I take these signals down here and I add them back up, I arrive again at my original signal. So we're going to experience a bit of loss in that fidelity, and we'll talk a little bit more about why later on, but that's the idea here, is we're decomposing some unknown signal into component sine waves and assigning amplitudes based on how well they fit through our data. So the next thing we want to talk about here is the frequency domain. So that's kind of when we look at it from this shifted perspective here on the side. So this is the time domain. We just see the raw values over time, kind of as a line plot. But over here in the frequency domain, we see the different amplitudes of the component waves. And this is helpful because it tells us what's happening inside of our series. So now we've got some cross-sectional data. So I've taken a window here, and I've applied this Fourier transform. I've pulled out these different sine waves from it, and I've got these different amplitudes. So now I know which of these frequencies are strongly represented in my data. And this is kind of what we're going to use to generate a model a little bit later down. So we've windowed the data, we apply the Fourier transform to pull out these frequencies, and then we have cross-sectional data here. And we'll see what that looks like when Marit shows us in the table a little bit later.
Okay. So I'm back in the workflow, and what Cory just explained is going to happen here inside the components. So let me open the component. Okay, so here you remember we had four different audios, 4 different TV shows. So we performed the same transformation 4 times. And as Cory mentioned, we apply the windowing on the signals, then there is the Fourier transform, and then there is binning. So let me go through these steps for this one signal, which is now the first TV show. So the output after the windowing looks like this. So we have come from the original 1 numeric column in the more than 16,000 columns now, and then we have the rows. And here each row now represents one piece of the music. So for example, 2 seconds. And okay, this is the first step, and I can go to the end of the table and I see, okay, there are still only numeric columns, and I need to do some other transformations. And the next one is to move into the frequency domain with the Fourier transform after applying the window function. But I will continue from here. So the configuration of the Fourier transform is actually not complicated. So I will go to the output, and here you see I have now the same, or not the same, reduced dimensions already, and the same number of rows. So the windowed signals here, and now each column in the output table is a frequency, and each value here in the rows is an amplitude on this frequency. And this is now the data transformed into the frequency domain. But the next step that we need to do is here, because we have these individual single frequencies. So we have quite a few columns still in there. We want to later combine signals from multiple, or combine the frequencies from multiple signals. So we need to standardize these. And we also want to reduce the number of columns a bit. So that's why we apply also binning, so that we don't have these single amplitudes, but we have the average amplitudes by a frequency bin. So that is what happens here as the last transformation step. So if I open the output here, I see here now that I have 70 columns. So I have reduced the dimensions, and I have now amplitude values representing a larger frequency bin than before, where I had only single frequencies here. So I think there are now 2 things that I would like to Cory explain a bit more in detail. So the first thing was that, can you explain a bit about the windowing? So what I am actually doing here, because I have now these rows, these are the pieces of the music. And I'm also interested in this binning. Maybe you can explain us how you do the binning of the frequencies here.
Of course. So let's jump back to the slides. And before we talk about the binnings, I just want to address really quickly that window function thing that we see there. So when we're applying the Fourier transform and we're trying to see which one of the frequencies on these sine waves fit really nicely to our signal here, we have something that can happen called spectral leakage. And this is when what we should see as a strong frequency here, for example, if we're like just generating one note on my guitar or something like that, and I know what the frequency should be, and I see it shifted a little bit. And that can happen when we window our data. So I'm going to take this opportunity to answer that question in the chat about windowing our data as well in a second. But when we window our data, we're just taking like a snapshot of it. So we had those 7 million rows in the beginning, and we windowed them just to look at the first, I can't remember exactly how many it was. I want to say it was 16,000 rows at a time. And we took that row, that 16,000 records, and we kind of pulled it up and pivoted it into one row. And then we had all of these rows that represented 16,000 or prior rows in our data, right? So we kind of took those 16,000 windows long parts of our original table and rotated them upwards. So there's another question asking if you use rolling windows or not. You can. I believe in our case, they overlap 50%. It's common to make them overlap in different applications here. And that's because we lose a bit of information at the edges of these windows due to this spectral leakage thing. So these windows typically overlap a little bit. But usually we do that just enough to cover the edges there. In this case, I think we overlapped them a bit extra because in a sense that helps us generate more training data later down the line. But yeah, when we window this data, we end up kind of cutting into it. So I kind of included this graphic here with a few different sine waves to show what that looks like. You can see that some of these don't complete their pattern. Like this one here gets cut off a little bit. This one's cut off a lot at the end. And some of these ones down here just kind of finish completely. Or maybe they don't start quite right. And this is what can cause spectral leakage. If I've got this sine wave in my data, but it doesn't quite match up, we can have some issues there because all of the waves that are calculated by the Fourier transform are waves that fit perfectly into my window length. So they're always multiples of this window length. So we see our amplitudes kind of getting shifted around a little bit because of that. So when we apply a window function, what we do is we smooth out the ends to 0. So imagine you've got a signal and it just kind of keeps going and it's an infinite signal. In that case, we can just apply the Fourier transform and everything kind of goes as originally intended. But when we're applying it on these windowed portions of our data, we want to kind of smooth out the ends there so that the sine waves can line up a bit better and we have less spectral leakage in areas that we don't want it. So the reason we do that then, in this case, is to kind of clean that up a little. There's a lot of different window functions you can use. I definitely encourage you to kind of look a few up. But a good general use window function is the Blackman window function. In particular, this one's really a great choice when working with audio data. And the reason for that is the way it smooths out our section of the signal is because it maintains a lot of the medium range frequencies. We maintain a lot of clarity on those ones, and we push our spectral leakage issues kind of off to the really high and really low frequencies, where there's typically not a lot of information in audio data. Now, this might not always be true. If you're working on a project where you're kind of trying to analyze really high-pitched screeches or things like that, maybe in machine maintenance, for example, you may want to find a different window function that specializes in maintaining fidelity on high frequency ranges. But for general purpose audio data, things that we typically listen to with the human ear, the Blackman function or the Blackman window function is a great solution for that. Another question kind of at this point, while we've got the graphic up here, is should the minimum window be at least the length of the largest wave? There's a formula out there for that, but I've completely blanked on the actual representation of it. So I'm going to grab that when Mara takes the screen next, and we'll come back to that question actually. but I believe it needs to be double. So we'll come back to that one now, so just hold that thought. But the next kind of question is, why do we do this? Why do we use the Fourier transform as opposed to some other transform? Because another thing we could kind of do here after we window our data is we could extract the mean, we could extract variances, we could look at all these different moments in our time series, and just pull out a bunch of information. And then we'd still be generating cross-functional data, right? We need to window the data and do something to it. But why is that something the Fourier transform? So the Fourier transform is really nice because it just plays very well with audio data. Because when we consider what makes up a sound, it's typically composed of sine waves, right? We think of music, for example, we think of the different notes you can play to compose a chord. Each one of those notes is at one clean sine wave. And when we play multiple on top of each other, we get kind of a messier wave that is a composition of several, and that's a chord. So when we're working with audio data or things that vibrate or oscillate or things that repeat, the Fourier transform is a great solution to extract information about those repeating patterns. So in general, if there's vibrations, if there's repeating oscillations, if there's sounds, the Fourier transform is a great way to extract features. And it's also a great way for that reason to kind of clean up messy, noisy signals, right? Because we can kind of extract the main components of that signal and then just recreate it from those main components, leaving the noise behind. Now that's not a perfect solution, of course, but that's kind of the idea here, is that we can extract from signals that we expect to be repetitive in nature, we can extract their key features. And then we kind of get to this binning thing that we talked about. So after we applied the Fourier transform, we still had like 8,000 rows. And that's a lot, right? We don't typically build machine learning models on 8,000 inputs. I mean, sometimes with deep learning, maybe, but it's certainly not a standard practice, right? So what we're doing here with this dimensionality reduction is we're binning these different frequencies. And if I go back a few slides, actually, since this isn't a great technical image, but the idea kind of holds here a little bit. If we have two waves that are really similar in frequency, so imagine I had another one next to this that was just slightly stretched out, it would match up with my original signal in a very similar way. So the idea here is that frequencies, similar frequencies should have similar amplitudes. And with that in mind, we like the idea of binning as a method for dimensionality reduction. So we can kind of look at these different bins. So when we do that, we're taking a few of the frequencies that are really close together and averaging their amplitudes. And we're kind of doing that in different ways. One thing that we did here as well is we used wider bins at the low and high ends of the frequency spectrum. And we used narrower bins in the middle range. So maybe we combined 200 or so different sine waves, averaged their amplitudes, and then called that a bin at the beginning. And then maybe in the middle, we're looking at just 100 different sine waves, averaging their amplitude and calling that a bin. So we're kind of moving around where we put that granularity here. And again, the reason for that is very similar to the reason that we're using the Blackman function here, is it just gives us more fidelity in the middle of our frequency spectrum, which is where most of the stuff that we can hear is. And since we're talking about data that's meant for a human ear in this case, we've chosen to assume that most of the relevant data is there. So that's definitely something to play with. It's definitely something to apply domain expertise to. I would probably focus more on the high frequency bins if I was working in a factory setting, for example, and listening for screeches, things like that. In general, though, we can apply whatever machine or whatever dimensionality reduction techniques we want. A lot of them still work here. Play around with them, see what works, but binning is a nice, safe option.
Thank you, Cory, for the explanation. So let me Let me come back to the workflow. And okay, so you answered my questions about the data, and you were telling me about the binning, that the binning is more granular in the middle than at the end. So let's check this. Here you see at the end, at the highest frequencies, I have at about 200, more than 200 hertz in one bin. And if I go to the beginning, it's the same here. So the first 200 hertz, they appear all in the same bin. But then you say that if I go somewhere in the middle, I will find more granular bins. So let's see. Okay, so there is less than 100. Okay, so I understand. So this is the final step. I now have my data for the classification. I have the numeric columns, the reduced numeric columns, since I have 70 predictor columns. And then I have as last here the class column, which says from which signal each row comes from. Before I move into the classification, I'm still thinking that I have here a time series use case. So can you just tell me where is the time dimension now?
Right. So if we think back to the window functions again, remember when we had one big series and we just kind of rotated it up, right? And created these different windows that were snapshots of our signal over time. So while we don't really have the time domain, when we're looking at these from the frequency perspective, we do know from which part of our original signal these windows are from, right? So we could track the changes in our signal over time by looking at the changes in these amplitudes as we go down our table rows.
Okay. So let's see this signals one more time. So we have here the visualization that you showed on the slide. And the final use case is to be able to differentiate between the different signals, 1, 2, 3, and 4, based on how the amplitudes are on the frequency bins. So this is the classification task. And as you see here already, just by visual exploration, they look different. So for example, on this frequency bin 20, the TV show number 1, it shows in average amplitudes at about 1. If you take a look at the same frequency band here for the TV show number 3, the amplitude values are at about 1.5. So there is a difference. And better than what we do here visually, the model is going to separate the different TV shows. So that's what we do here at this part. We have trained the gradient boosted trees model to predict the source, so the TV show, based on the frequency columns. Okay, then we apply it to the test set here, and we see the results. So here they are. And if I take a look at this overall accuracy here, I see that it's more than 90%. So for almost all of the signals, the model is able to predict which TV show it is coming from. So this actually finishes the use case here. We have now a workflow for audio signal classification. I think you can also download it from the hub for you, and you can test it yourself. But maybe you, Cory, also have some other use cases for this audio signal classification. What could I use this for if I now learn to practice with this?
Yeah, thanks, Marit. I just wanted to circle back to that question really quick while it's still fresh. I did double check, and I see a couple people confirmed in the Q&A section for me as well. Yep. When we're looking for the window length, it should be at least twice the highest frequency that you're expecting to pull. So if we had a window of length 100, the highest frequency we could extract would be 50 hertz. So keep that in mind. If you're looking for 10,000 hertz, you'll want to have at least 20,000 records in your window. And that would be a really high frequency, but yeah, so that's the correct scalar there. Okay, so next we wanted to talk a little bit about where these types of applications typically pop up. So the Fourier transform is used in a lot of different places here. We've used it for forecasting purposes. We've used it for anomaly detection. We've used it for machine maintenance. We've used it today for a classification model. So it's really used anywhere we're recording time series data. So the topic of today's discussion has been on really high frequency recordings like audio or vibration sensors, really just IoT stuff. But the Fourier transform is used in other ways in much less, much wider time series data, right? So we can use it on daily data, we can use it on monthly data. And that's a common way to extract pattern sizes from your data. So it's used across kind of across industries in that way whenever we're talking about time series. But its most powerful applications are certainly in this IoT signal space. So we see it being absolutely invaluable to things like machine maintenance or voice recognition, or of course signal classification like today. If we wanted to pull in electrical signals and kind of analyze what those were and where they're coming from, we can work with that as well. So there's a lot of different places we use this. We've talked about it a little bit with anomaly detection as well on some of the NIME blogs. We haven't talked too much about using it for signal cleaning yet, but we did touch on that a little bit. It's a big use case there if we want to extract noise, right? Because we extract these sine waves, and then if we kind of add them back up, we get a recreated version of our signal that only contains the most notable aspects of it, right? So that's a good way to clean up our signal and extract noise from really low amplitude frequencies. And that's how some data compression algorithms work as well. So you see it used a lot in that space when we need to do apply compression, because we can represent so these signals in a fewer number of terms. So it's very useful in a lot of different spaces for a lot of different reasons. Just to recap kind of how we did that today, these were kind of the three key nodes, and these are part of a NIME extension. So the easiest way to get these nodes would just be to click on one of these links, go to the NIME Hub, search for them, and just kind of drag one into your NIME Analytics platform, and it'll automatically prompt you to install the extension. But the extension, I believe, is called Signal Processing, and it's by AI Associates, one of our partner companies. And what these three nodes did, again, just to recap, is this first one allowed us to specify a window length and also how far down our table we move. So that's kind of where we can configure if we want these windows to overlap. And it kind of shifts those rows up into sets of columns. And we need that before applying the Fourier transform over here, because this one's going to apply that transform row by row using all of those columns as inputs. And I remember there was a question somewhere about how we reduced the number of rows from millions to hundreds or maybe thousands. I'm not quite sure how many rows it is. And that's when we applied this window slider. We had very wide windows. We used window lengths of 16,000 or so, which allows us to capture frequencies up to 8,000 hertz. So that's kind of where we saw a lot of reduction in the number of rows. But then we had a very wide table that was 16,000 columns wide. We applied the window function, which kind of smooths out the values to 0 at the edges of those windows. So my very first columns, my very last columns kind of go to 0 there. And that helps us remove some of the spectral leakage that we don't want to have messing up our narrow bit of information at the middle of our frequency band. And then we applied the Fourier transform. And this just kind of took our input columns, applied the Fourier transform to them, and then gave us as an output the amplitudes to those component sine waves. And this was another spot where we saw the reduction in data size. Because when we apply the Fourier transform, we only get half as many terms as we put in. So this is kind of where that rule about needing 2 times the number of your highest frequency, is we need to see that pattern show up here. And that's going to be part of how the Fourier transform is calculated here. And we need that double the size of our highest frequency. So that's where that half reduction in columns comes in. We applied the binning fairly aggressively, bringing us down just to 70 columns. And at that point, we had a fairly small table that was really easy to train a model on. So just kind of reminder that these are the 3 important nodes that kind of enable you to apply this Fourier transform and get to a space where you can build a predictive model. So just these 3, we transformed our data by windowing, by smoothing, and then by Fourier transform. Okay. And then this example today, there's a lot of nodes in here that can be kind of difficult to plow through in a 45-minute session. But we really encourage you to go to the NIME Hub, grab this example, and kind of play with it. Grab the parts of it that you need, reuse them, change things, try different binning techniques, maybe even try different window functions and see what happens. It's a really interesting tool to play with. It's really nice to be able to apply some of these operations really smoothly with these NIME nodes and see what happens. If you haven't downloaded NIME already, we definitely encourage you to do so. You can just go to nime.com/downloads. Go to nime.com/learning. You can get some more resources there. There'll be information about other time series courses that we offer, as well as opportunities to kind of get you up and going with NIME AP itself. But yeah, download that, check out the hub, download some examples, and come talk to us on the forum. You'll be able to find the slides and all of the useful hub links on this forum thread for the webinar a little bit later today. And we'll kind of open it up to questions here.
I think before you stop sharing, there was a question to repeat the idea of leakage.
Sure. Oops, wrong way. So I'm not going to talk too much about the leakage and the window functions here today. But what these window functions do is they don't strictly reduce the amount of leakage that we experience, but they kind of shift it around a little bit, which can be helpful when we know that there's specific areas in our frequency spectrum that we want to look at. So in a lot of this spectral leakage comes up because of windowing. When we window our data here, we end up kind of cutting into pieces of the signal. All of our sine waves. I think of a good way I can draw this. Can I draw on PowerPoint? I think I can, right? Bear with me. Okay, well, I'm not going to do that right now because I'm not sure how. But the idea here is that when we're looking through all of these frequencies that we run through in the FFT back here, these are all these are the frequencies that we're actually applying here. Our I 2 pi over n. N is the number of terms we have, and then the number we kind of iterate up through those. So if we've got 100 different, or if our window size is 100, the different frequencies we try are this 2 pi over 1, 2 pi over 2, 2 pi over 3. So we're taking the full length of our window and we're dividing it into 1 wave, 2 waves, 3 waves, 4 waves, and so on. So all of the frequencies that we try to fit to our raw signal are clean multiples of our original window size. And because of that, we end up getting some leakage there, where things that might not actually be good fits do seem to be good fits, because this sine wave, for example, doesn't quite fit. This one's cut off a little bit. So it might not get fit to the proper, the closest possible like time frequency. So what we do to try to help out with that is we kind of smooth all of these ends to 0. And that helps make some of these fit a little bit better. One thing that might be awkward for is really high or really low frequency waves, depending on which windowing function we apply. But in this use case, we're not terribly concerned with that because a lot of the information that we want to pull out are from these kind of middle of the road sized frequencies. Yeah.
Okay, thank you. I hope this answers your question. The next question is there a node to play the sound data or sound files?
I do wish there was. Originally, there is a wave file reader, I believe. I haven't used it much. I would go to the hub and search .wav. That's the file type, and see what you can find. I don't believe so. You could probably push them back to a Python script and get some sound to play from them. But yeah, unfortunately, we've converted them to this table format now to make them easy to use in this example. So there a little bit of file type manipulation would have to go down before anything would play them. That being said, a wave file is literally just a list of numbers inside. So transforming it back is no messy procedure. It's more of a matter of being the proper file type. Yep.
Thank you. Okay. Next question. So it's about the window size. Why is it the high frequencies that require a larger window? Is it? It seems to be a bit counterintuitive. I don't know.
Yeah. So if we go back to the Fourier transform for a second, it kind of comes down to what we're looking at here. So if I had, again, say a window size of 10, the highest value that goes into here would be 1/10. And when I'm looking at that here, those represent the higher frequencies. So that would represent the wave that is produced 10 times inside of here. And because these frequencies are per second and not per window, we need wider windows to pull wider frequencies. I'm not sure that I'm super happy with that explanation, but that's kind of where we can see it most clearly right now, is by looking at the Fourier transform equation here. The largest frequency that we fit is 1/, the maximum size of the window. And that kind of comes down to the issue with it being discrete again, right? So I talk about I keep looking back at this one, but these are continuous. But if it's discrete, it's harder to track a lot of like oscillations without having more data points, right? Because we need, wish I could draw on my screen right now. I need to find a way to do that for next time. But imagine you've got a sine wave like here, and you can tell that it's changing direction. The only way to tell that it's changing direction is to see that it's coming down and then see that it's going up. So it requires basically 2 data points to see a change here. And that's why we need 2 data points per hertz. I don't know the best way to say that. So we need 2 here to see that happening. So the higher the frequency, the more data points we need, because we need to see more turns in the signal. Hopefully that helps a little bit.
I think that was a clear explanation. I hope this helps also the who asked the question. Now that you're on the slide where you have the formula of the Fourier transform, there is another question which says, where in this formula can I see the input and what are the other things? What is an
Yeah,
estimation?
let's run through that one more time. So the first thing is, I guess we'll go left to right this time, is this x prime over here. So these are the transformed values. So in fact, these are my amplitudes. These are the values once I get into the frequency domain. And this xk over here is my original time series. So these are the originals and these are the transformed ones. These ones represent, let's see. So the xk's are basically the recordings of this wave, and the xk primes are these amplitudes over here. So these are the amplitudes down here. Okay. This exponential here, these are my different sine waves. And what we have in the middle is this dot product. So what we're doing is we're multiplying the terms by the value that you would get from that sine wave at that point and saying how close are they. So if this one's high and this one's high, you can see that I would get a high value. If this one's low and this one's low, I also get a high value. But if this one's 0 and that one's high, I get a low value. So in that way, we're kind of using that feature of multiplication, I suppose, to correlate the sine wave to my original signal. Because if they're both high, then I get a high value here in the sum. But if they're not both high at the same time, then I get lower values. But yeah, this is the original signal. This is the frequency domain, and these are the different sine waves in their complex form.
Okay. Then there is a question, not a bit more general. So is this Fourier transform working only on regular signal, or is it can you apply it to any kind of uses the word chaotic signal? Yeah.
So in general, I would say that you can apply it anywhere. I'm not going to say that it's always going to be useful, right? So one of the things I kind of touched on earlier was that it's most useful when you suspect there are underlying repetitive components that, like this one here, we can clearly see that there are some oscillations that are repetitive. So this is kind of, I mean, it's a toy example, of course, but when we suspect behavior like this in our signal, that's when it's great to apply the Fourier transform, because what we extract are exclusively these repetitive patterns. When we talk about maybe chaotic or noisy signals, this is an application for cleaning them up commonly for the Fourier transform, because we'll extract these kind of key features from our signal. And if I just imagine there was some randomness on top of this signal here, I'd still mostly see these ones pulled out. But if I added them back together, I wouldn't quite get here. I would get a cleaned up, denoised version of my original signal. So that's an application to it when we're talking about noisier data. And while I'm talking about that, I saw a question about whether or not we need to decompose. I would remove trends before applying the Fourier transforms. So definitely detrend your data first, at least. And as always, when you're applying kind of extra techniques, it's good to extract whatever you know first to kind of point the techniques that you're going to apply at the unknown, right? So the things that you do know about, I'd extract those first and then see what extra you can extract. But the trend is particularly important to pull out because, as you can imagine, you can't really represent a vertical trend line, right? Like the line y equals x. You can't really represent that as a sine wave very well, right? So things that couldn't be represented as sine waves that you know about, like a trend line, are great to remove beforehand, and they'll give us more fidelity when we actually apply this transform.
Thank you. Actually, there was another question about predictive maintenance. If we have workflows, example workflows on that, and we have. So if you search for anomaly detection for predictive maintenance in the NIME Hub or in the NIME blog. So there is one, and they actually work directly on Fourier Transform data. So there we don't show the Fourier Transform itself, but the anomaly detection part using the Fourier Transformed signal data, which comes from some sensors monitoring some mechanical piece. So I will post the link at least to the person who asked for it. And
yeah, the other thing I'd like to encourage everybody to do is go check out this forum thread. And I can show you actually really quickly where that would be, just in case the link is difficult to track down. Let's see. So if you go to the forum.nime.com, and then you click over here under resources, events, you'll see different threads for our different events that we host. And we're right here. We're this webinar moving into the frequency domain. So we'll make sure to post as many of these resources as we can remember after this wraps up. You should be able to find them all there. It's a great spot to kind of continue the discussion as well. So we'd love to see you come join us for that. And I'm actually going to try to copy this and see if I can and paste this into the chat. I don't think you guys can type in the chat, but I believe you can see it. So let's see if that works. And we encourage you guys to kind of bring more follow-up questions to this thread, and we'll post a lot of the material there as well. All right. Any other questions for us today?
so if you don't mind going back to the workflow and to the technical questions, then I have actually to the data access. If you know, how is the pressure extracted?
So how, I guess that's not really a question that I'm an expert in prepared to answer, but that's what a microphone's for, right? A microphone is just a pressure sensor that checks pressure in the ambient atmosphere and records a value. I think those typically work by recording a voltage. The different pressures, maybe push two plates closer together, allow more electricity through, we get a higher voltage, and we correlate that to a higher pressure around the microphone. We record those at a very high frequency over time, and we can recreate a sound wave that way.
Perfect, thank you. Then another question is, maybe we can take this as the last question. So if you have how do you do binning if you have very varying frequencies in the neighboring, very varying amplitudes in the neighboring frequencies?
So that's expected. If you go back and look through our workflow, you'll probably see that that's happening on some level. But we're not terribly concerned with that right now, because our main goal here is to reduce the dimensionality and use it for a classification purposes. And often we can do that just by saying, like, oh, this signal's got a lot of frequencies that are high, like there's just a lot of high amplitude frequencies, or I'm sorry, there's a lot of high frequency waves that are representative of our data. So it's not typically necessary to worry about that too much. But if you did want to, when we bin these different groups of our frequencies, we could extract more than just the average, right? We could bin them and extract the average, the max, the minimum of the variance. You could extract more of these terms if we felt that would be helpful to our process down the road. But in general, I wouldn't worry about that too much. It's expected. It's not necessarily ideal, but it's a very effective way to reduce the dimensionality of our data here, because we do expect some similarity in those similar frequencies.
Okay, Thank you. I think the next questions that you have, you can post in this forum thread. And I think it's time to say thank you from our side for joining.
All right. Thank you, everybody.